All right, Johnny, you ready for another episode of the Future of Data?
Of course.
Well, today we have a fun one on popular demand from our community. We are going to follow through and chat about confidential computing today. So, you guys know our perspective here at Weavechain. We think that Web3 data is a first-class citizen with a lot of cool properties like verifiability, but also the future of data economies. We think it is going to be based a lot in confidential computing patterns where you're not going to have people that are actually sharing data with each other as much as sharing access to data to run computation and get results without breaching privacy. So we have enabled a variety of different patterns with confidential computing at Weavechain, and basically we're just going to go and talk through them all today. So, the first one we'll chat about is really simple, just data obfuscation and redaction, quantization. These are the techniques that have been used before a lot of this other fancy technology has come about. And the general idea is that, people have been sharing sensitive information, for example, like patient data at hospitals, for a very long time. Now, you can't do it in a raw format because that breaches patient privacy. But what if I was willing to say, okay, look, I'll give you access to my entire medical record as long as you don't have my name associated with anything and I can't be identified? People have said that that's okay. There's like big parts of HIPAA around how you do this confidential sharing. And the general idea is that let's say that I have a Weavechain environment over here that has a table for patient data. And we know that we can't just go and share, my medical record with Pfizer when they're doing a study because that breaches my privacy. Historically, what you do over here is come over here to a name field and say, I'm going to replace all names with a blank field. The problem with that scenario is that then, if there's a lot of different, let's say, data rows in our table that were all associated with my user, we can't actually see trends in my user over time, right? We can't go and match up, let's say, my blood work from 2020 with my blood work from 2021 or anything like that. So, if you take this one step further, we would say, okay, I'm going to go and replace all names with a numeric ID so that, everybody is patient 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, as opposed to being patient Omar Alnigar. And a hash is a similar thing where instead of like a friendly number, 1, 2, 3, 4, 5, we're going to replace it with, what is it, Johnny? Is it do you do salted hashes here or just a regular hash?
A salted hash. And also the numeric IDs actually has you can have a unique per table, or you can have a linked numeric ID that across tables is the same if you need to do joins. So we also support that. There are of course also more advanced techniques like canonizations, and currently we do not support canonization, but we do support a lot more than is listed here.
Yeah, maybe you can talk about some of this. So, what's the difference first off between obfuscation and redaction?
Obfuscation, well, redaction is a type of obfuscation after all. Redaction is replacing a piece of data, sensitive data, with some predefined content. And you can have hard-coded, let's say, replacement for a certain value. You have another replacement, or you can have rules. You could set up an entire set of rules how to do the replacements.
So like this numeric ID would be a form of obfuscation.
Yeah.
Where we're like hiding the name with something else.
Yes. In particular, the numeric ID approach is replacing values with a random numeric ID. Mm-hmm. And as I said, it could be consistent across tables, or it could be unique per table if you want to break the associations.
Right. And, like the associations are actually quite important. I think there are a few companies out there that do nothing but manage these associations between data sets. I think Datavant is actually very famous for this. They will go and make it so that you can have anonymous user data, but that can associate like your electronic health record with your insurance payment, so that we can go and draw some correlations on that front. To do that, you need to go and have that consistent ID across those fields, right?
Yeah.
And then, so how's it different from redaction?
Redaction is replacing some content with another type of content based on some rules. It could be, as I said, a simple rule that replaces any name with this text, or you can have some rules around it, such that, I don't know, let's say you don't work with names, you work with conditions, and you still want to probably, I don't know, obfuscate the particular condition, but still have a category, for example.
Could it be as simple as like, buckets? Like, I'm going to take all blood pressures from 60 to 70 and make it 60, 70 to 80, make it 70. Is it that kind of thing where you're just defining some simple rules? Cool. And then, last but not least, what is quantization?
Quantization refers to, so there are two sets of variables, that categorical variables and for time series for numerical variables. We do quantization. The quantization is replacing the values of the time series with, let's say, fewer discrete values, such that you cannot identify somebody by matching his medical records and seeing that he had an exact value of some measure. It's, let's say, rounded to some number. But there are also transformations that can happen, or splitting a value, doing PCA or doing some transformation and projecting the value on multiple axes. And then you can quantize and also quantize that. The whole idea is to replace the actual values with something that with buckets, let's say.
Yep.
And in addition to quantization, we also have transformations that can happen on the data, as I mentioned, linear or nonlinear, and noise addition. So although it's one variant is to keep them in buckets, the other one is to also add some noise. And that's a way to still obfuscate time series. The whole idea is to break the link to the original data such that somebody that has the data cannot trace back the person.
Well, that's the key thing, right? And it's actually quite hard to do that and still derive a lot of meaning from the data in a lot of scenarios. For example, like, I am a 38-year-old male who has a child and lives in Oakland. If you go and look at enough of of the data, even if my name's not there, you might be able to re-identify me, right?
Yeah.
And in all these scenarios, whenever you are giving somebody a data set, even if you have used one of these techniques, there's always a high risk of re-identification, right?
Yeah. Given enough dimensions, you can zoom in to somebody if you apply a lot of things. That's why you need another step of let's say obfuscate. So still there are a lot more methods that can be applied. You can chain different methods of obfuscation, but no matter what you do, you are still vulnerable at some point.
For sure. So then let's move to a more advanced technique, right? Compute to data. And let's say in the rest of these scenarios, we are never going to share any of the raw data, right? It's the difference between over here saying we're going to do some fancy things with some of these fields to make it so that hopefully you can't re-identify people, versus saying I am not going to give away this data at all. I will just make it available for remote computation. So we like to talk about computed data first, just because I think it's like one of the simpler concepts on this list to sort of grok. And I'll try to walk this through it in a couple different little vignettes for you. So let's see over here. Let's stick with our hospital scenario and say that a hospital has all this really interesting patient information that drug discovery companies could use to go and find the next cure for COVID kind of thing. But they can't share the raw patient data. In a computed data scenario, they would say, okay, researchers, we will get you access to a schema of the data and maybe some sample data, and then you design your analytical process, and then we will allow you to submit your compute to run locally at the hospital server, and we're just going to give you the results, but not the data itself. And at Weavechain, we're really big into this idea that we would have a secure record of how this data was accessed and by whom and the results, and then also make it available for compensation. I actually like the team at Bacalhao's slides for describing this. So props to David Aronchik and the Bacalhao team, because I think this is beautiful. Again, the idea is that the researcher over here wants to get access to this data, and the hospital, if they're going to allow somebody to run computation on their servers, it's actually very important they know what code is being run, because we talked about the risk of re-identification earlier. What if this code's whole purpose is just to go and like return a table of all the raw patient data? That's not a good scenario. So ideally in the computed data scenario, the hospital actually goes and validates the code first, and then goes and runs it on the data and gets some results. And then you actually want to go and audit the results also to make sure that no data exfiltration has happened. So there are ways to do this programmatically. Johnny, what are your common techniques here?
So there are several ways to check the data. You can, let's say, limit the size. It's a good safety measure to limit the size of the output.
Yeah, if you're running like on 1 GB of data and
Yeah.
then only 1 MB returned, it is very unlikely that you have exfiltrated a ton of bad stuff.
Then you can have inclusion and exclusion filters. You can force the output to follow a certain template. Multiple filters on the output field. But the problem is that no matter what you do, if you don't audit the code, and there is, let's say, an infinite, another thing we do is to have some rate limiting, dynamic rate limiting. But you have an infinite number of round trips between org B and org A, and the result is, let's say, is not audited enough. I mean, there's always a way, either encrypted or with steganography, with something to exfiltrate some new information from org A with org B. And you can exfiltrate the data using the features that computer data offers. But then again, there are different ways to do it. The most flexible one is with Docker images. It's also the way Bacalhau does it. We also does it with Docker images. You can also have WebAssembly, which limits a bit more the thing that you do. So you have much more control on what that image can do.
But let's say, like, I think compute to data is one of the most flexible techniques out there, because you can literally run like whatever code you want. The problem is it's quite cumbersome, right? You need to go and be really confident about the code that's being run, how you're going to let it happen, and then even the results over here.
I wouldn't say cumbersome. It's also the most flexible and the easiest to use, but it has some privacy issues that you have to do. I mean, even when starting Docker image, you have to take care to isolate its network. There are a lot of possible problems that can arise.
Yeah, exactly. I mean, you're running letting arbitrary code run.
Yeah, but so, if there are if you can audit the code, that alleviates the problem in
yeah, for sure. But some of these other techniques are designed to go and prevent some of those issues from happening. So let's take, for example, multi-party computing. I think one of the key ideas for multi-party computing is that we're going to go and enable, let's say, the analysis to be happening on top of multiple data sets at once, and also be running simple algorithms for it. So let me see. I think I have a nicer slide over here. Let's say that we were going back to our original concept of compute over data. This is by definition one-to-one, right? I'm going to go and allow one party to go and run code on another party's servers.
Correct, but you can multiplex it. So we have this feature to send the same Docker to multiple nodes, get the results, and aggregate them on. That's one. And also,
would you consider that a form of multi-party computing?
No.
It's different, huh?
No, it's totally different. But also sending the same Docker to multiple parties that can have the same data can yield a consensus on the results. That's another use case. The multi-party computing is a way to compute something across multiple machines without any machine learning anything about the data on the others, including the recipient, so the task launcher.
Yeah, exactly right. I can show our example on this really quickly, and then maybe you could talk through this scenario and how we would do it. But let's say that we had enabled this data set just for confidential computing over here. In a multi-party computing scenario, we can go and connect to our Weavechain node. Let's say that there's some data that's available for naked access, but not patient data, right? Patient data is not authorized for just read operations. We could, however, run a correlation on that patient data by saying, run multi-party computing for this simple algorithm, just a correlation algorithm. And we get one number down here. Go ahead, John.
Incidentally, this notebook runs in a single node, so it's a single party computing. It's a degenerative form, but the exact same code, if it was launched on multiple nodes, the same code would have computed the correlation on multiple data sets. Underlying, so Weavechain is wrapping the SPDC protocol from Alexandra Institute, so the implementation from Alexandra Institute. And what we do is to offer this wrapper that it's using our transport mechanism and also our integrity guarantees. So we have a layer that does lineage on top of what's computed. And we launched this protocol across multiple parties, and we return the results.
Yeah, and I think that's the beauty of this vision over here, right? We could be running a study across the data that's available from multiple hospitals, and even like, if individual users were holding their data locally, we could still go and do that exact same correlation with the exact same builder experience. It's just about what data is actually connected to the Weavechain mesh.
If we are to compare it with Docker images, so this one, for one thing, allows running on multiple data sets without the parties learning anything about their data. It's also running a limited number of algorithms. So the algorithm that runs needs to be implemented. It can be implemented by Weavechain or extended as a plugin, but there needs to be some code that uses the protocol to implement the function. And it's, let's say, safer than a Docker image because you know what you're running. So it's being, let's say, a linear regression. You know that it's only that linear regression. It's not, it cannot access anything on your network. It cannot do anything else because it's
exactly. Like these are the operations that we support for multiparty computing: correlations, inner product, linear regression, mean, median, standard deviation. Can you define which of these you're actually going to have to run, or do we do all of these?
We do all of these.
Yep.
And
but again, it's
the thing is that you have to extend the code in order to support more. While with a Docker image, you have full flexibility of any language. So
that's right.
Actually, any language that supports our API.
But this is like an easier way, I think, for people to go and be able to run studies on data that they can't see in sort of a bounded fashion, where it might not be quite as cumbersome as the auditing of code for computed data. So, just to get back over here, multi-party computing, very powerful, can use a lot of different endpoints, but the functionality is actually a little bit more limited for good and bad reason. Now, how about homomorphic encryption? I guess this is a little bit more similar to a computed data scenario, right? I think you'd only do it in a one-to-one situation.
Yeah, it's a one-to-one, but it's let's say, so also MPC uses somewhat homomorphic encryption. That's the actual name of the. But back to the homomorphic encryption. So its use case is a one-on-one when the party that's doing the computation does not want to reveal its algo. And the process is something like the party that wants to use the data makes a request for the data to the data owner. The data owner can provide certain columns in plain text or obfuscated, let's say, and certain columns in an encrypted format. So the numeric columns in an encrypted format.
But I'll start here really quickly. The challenge is that in a computed data scenario, we said that the owner of the data needed to look at the code that was going to be run. And in homomorphic encryption, the owner of the data does not get to see the code, right?
Correct. And also homomorphic encryption always one-to-one. It's this particular implementation, it's one-to-one.
I see.
So as I said, also multiparty computing is using somewhat homomorphic encryption. So it's one-to-one.
Yep.
So I wouldn't say that it's always on one-to-one. This implementation that we have, it's one-to-one.
Yep.
So let's say the people that need to run something request the data, they get it in an encrypted format, and they can do transformations. On linear transformation mean that you can do additions and multiplications, or build a neural network because it's additions and multiplications, or many other algos, including boosted. You could implement boosted trees with homomorphic encryption. The idea is that your algo does these operations that are unknown to the data owner. But at the end, once you have the result, your result is also encrypted. You cannot see it in plain text. So you have to return this result to the data owner, and the data owner sees your results, eventually audits them, and gives it back.
Receives encrypted results.
And it's releasing the data to the party performing the computation. For the homomorphic encryption, we wrap SEAL and the EVA Python wrapper from Microsoft. This is actually a CKKS homomorphic encryption. There are various ways to do it.
Just to finish up this bit over here. So, end result. Consumer gets results. Data owner didn't see algo. Consumer didn't see raw data. Right? So back to the libraries that you said we're using. It was Microsoft Seal is open source for homomorphic encryption. And then EVA was, what was the purpose of EVA?
It's a compiler. So working with Seal is quite cumbersome. You can write code in Python and compile it with EVA to Seal.
Yep.
To be used by Seal, let's say.
And then you've been mentioning earlier, there are only certain forms computations can be run with
linear transformations.
Yeah.
This is you would use this if you have a, let's say, secret trading algo that you don't want to reveal to anyone, and you need to come to backtest it with some data that you have. I mean, on some data that somebody doesn't want to share.
Yep. And what are some of the other drawbacks of homomorphic encryption? It's pretty slow and
speed is a problem, and also the fact that, or at least until CKKS, it's actually better. But you can do a limited number of operations until the noise. I mean, all the lattice encryption. So there is some noise added in the process, and that the noise becomes too big, and there is some normalization that needs to happen. And CKKS alleviates some of that.
Are there other problems with homomorphic encryption for like size of the data sets?
Not necessarily. It can be a problem. I mean, also MPC has a problem with the size of the data and when the number of parties is increasing a lot. Also, homomorphic encryption has a problem of speed, but the size of the data is a problem only because working with encrypted data is slower.
Okay, so speed is the big problem over here.
Yeah, but I would mention that, so multiparty computing is one thing, and let's say we should say it's multiparty single-party computing on a limited set of algos. So running a single-party limited algo is quite simple and in a way different than computed data, and could also work and has no speed issues. But obviously, then it's not truly multi-party computing and not that interesting.
Interesting. Cool. Well, time is flying. These are clearly some complex subjects that we're running into. Let's jump into federated or split learning.
The federated and split learning are just two methods of training a model on a distributed data set. On the federated learning approach, each party is training something, and then the results are let's say a neural network is trained on multiple machines, and then the weights are averaged. There are different ways of aggregating. Split learning is another approach that does the same thing. It trains a part of the model on the machine and then continues the training from a certain layer onward on the source machine. So it's, instead of training the models and averaging them, it's training partially on each.
let's slow down just a little bit and finish just talking about federated learning for a second. This is the core concept, right? It's I need to go and train an AI model, and I want to go and train it locally on each one of these devices without the server ever having the full data set, right? So it is just another form of, let's say, this diagram that we had over here for specific for machine learning training, right?
Yep.
And then you said neural nets are commonly trained using this method. Are there any other like key bits to federated learning before we jump to the split learning part of it?
No, I think that sums it up. And there are a lot of variants of federated learning. There is also federated learning with homomorphic encryption.
Oh, really?
Yeah, it's a huge domain.
Yep. And then,
yeah.
And so split learning is a different take on federated learning, right? And I think this was pioneered by, I think Ramesh Raskar and the MIT group
Yes.
did a lot of the foundational work here. But maybe you could describe what is the difference here? I think it's all about the smasher, right?
Yep. So the training is happening partially on the edge and continued on the let's say the task launcher.
What do you mean that the training is happening on the edge? Is it that it is going to
on each device? So a part of the training happens on each device.
Yep. As opposed to how does it work in federated learning differently?
The whole model is trained on each device, and then the weights are aggregated using some aggregation algorithm.
Each device. You said for federated learning, the whole model is trained on each device?
Yeah, the neural net, for example, is trained on each device. And then the simplest something is averaging the weights from.
Interesting. And what are the advantages of split learning? Is it that it's faster, easier to implement?
Not necessarily. I think also has some to train how fast your model converges.
Speed of training?
Yeah.
Super cool. But these methods are really for how are you going to go and train AI models, as opposed to like how am I going to go and get a results back from like that correlation between those two things, for example. Cool. Well, I know we're really at the end of our time here, so let's just really briefly jump into zero knowledge proofs and Merkle summation trees. And zero knowledge proofs are a very hot topic right now in regards to how they're being used to support blockchain technology and roll-ups for greater efficiency and speed. But I like to go and just we have a fun example in our demo over here where we go and use zero knowledge proofs for debugging a data set that you can't see, for example. So over here, let's say that we wanted to, oops, sorry, this is not the book. Here we go. So again, we went and trained our machine learning model on these patients. We could do things like understand the importance of alcohol use on cancer severity. But if, let's say that I see results that I don't expect, how do we go and validate that the data set's actually okay? In this case, we're using zero knowledge proofs for debugging and saying, let's go and create a zero knowledge proof for each patient in the data set that their page does not equal 0. And, when I run this function to verify those zero knowledge proofs, I go and basically just get a bunch of true statements for each of these. The magic here is how would you describe it, Johnny? It's that we can't.
You get a statement. You get a statement about the data without seeing the data, and you have it's actually a provable statement.
A provable statement, right? Now, in this case, how is it being proven? It's that the data holder is executing the certain code against it to validate it?
So the data holder is creating a proof for and it's a niche use case of zero knowledge proofs. You could use them for a lot more things, like I think it probably is the best known topic from all the ones that we touched by our audience.
Yeah. Maybe we'll have to go into zero knowledge proofs again next time to go a little bit deeper. I think right now with our API, you made open source both our Java repo on bulletproofs that was based on the rest of implementation, and then also a bunch of the gadgets that you built using it, right?
Yeah.
So and the idea is that you need a different gadget for each different type of thing that you're proving. So over here, we looked at numbers non-zero as a gadget. We also have like, numbers within the range, for these parameters.
Right. So we open source the bulletproofs. So currently we support bulletproofs. The aim of Weavechain is to support any type of ZK proofs. So snarks or starks or anything. So the aim is to be let's say aggregation layer of technology and be able to generate proofs. Maybe you need snarks, and then you should be able to do it with the same simple API call by just changing something in the parameters.
Beautiful. Cool. And just to emphasize here, we have a list of all of our zero knowledge proof gadgets in our docs. And you guys saw that repo on GitHub for both the proofs and the gadgets over here. I think we're gonna have to go and do a deeper subject on zero knowledge proofs next time. But we'll just really quickly to summarize the last topic here of a Merkle summation tree. And I actually like to use Binance for this one. So after FTX blew up in November, people were sort of demanding that major exchanges go and list a proof of reserves, where they would go and basically make verifiable attestations that they had more assets than they had liabilities for the products that they're offering. So in order to do this, Binance goes and creates what's called a Merkle tree from every one of the positions of the users in its network. So if you had a account at Binance, that balance would be used to create a hash, and Merkle trees will go and take multiple hashes and take hashes of those groups, and then eventually come to this root hash at the top that is posted in plain sight, timestamped at these different intervals. Every month they're going and putting one over here. Now, as a user, what you want to be able to do is say, okay, look, if I can come in here and see the hash of my position and balance, then I should be able to go and use that and download the Merkle tree and verify that my position is actually in that Merkle tree. They used to have the open source code over here for how to actually do that. I don't see it here at a glance, but I'm sure it could be identified over here at some point.
I think they changed it once they switched to Knux.
Interesting. Does that make it so that an individual?
Yeah, but it's still open source. So
it's still open source.
Yeah.
Got it. Cool. And we enable the creation of those at Weavechain as well. So we were using it for our product Accountable that is doing these kinds of verifiable portfolio calculations for a variety of different purposes instead of just proof of reserves. But the general idea is that we have a table with a bunch of positions over here, and we make it so that you can go and really quickly create a Merkle tree from that data with a few Weavechain calls over here, right? Create Merkle tree from this table, and then go and see how those hashes roll up to that Merkle root and visualize it. Then we go and put that root on the blockchain so that people can prove that it has never been tampered with. Sorry, go ahead, Johnny.
Yeah, so actually we have this feature to create Merkle trees programmatically, or we maintain a red-black Merkle tree and we maintain it live on the table. So we can have this feature enabled so that anytime there is an update to a table, you get the Merkle root rebuilt live and the root hash published.
We love that, right? This is part of maybe next week we'll go into a little bit of the AI lineage scenarios for showing these proofs, but the concept that you're going to go and have every update creating these new Merkle trees and anchoring it to the blockchain is really powerful. It's sort of much faster resolution than the Binance method, which is once a month kind of thing. And the question is, what kind of verifiability will be demanded of data in the future? And I think these are still open questions right now.
The main idea with the Merkle tree on data is that you are able to check the inclusion of a piece of data in some aggregated result. And this applies for, let's say, what Binance did, proving the results, or in the AI case, you could check, for example, that a neural network was trained with something, and your data, some copyrighted data that you own was included in the training set or not, for example.
You got it. Well, obviously, we needed to go in and put way more time on the calendar for all these different subjects today. But let's cut it there for now. Johnny, thanks so much for joining me on this one. And we'll go and post this in the chat with a few other questions, and happy to dive into more subjects on this soon. Thanks so much, everybody. Until next time.